I'm Joosens. I'm a PhD researcher at ID Lab, which is a research group at the University of Antwerp in Belgium, far away from here. And we also are affiliated with IMEC. You might have known from their chips. And today I want to talk about an implementation I did of a multi-channel DASH7 receiver, transmitter and receiver, to do some packet investigation and validation with GNU Radio, of course. So, Internet of Things, you might have heard from that as well. Typically, what they want to do is, have some low-power devices which go long ranges, and of course, operate in a narrow band for most of the time, sensor communication. Most of the known technologies you might have heard of are like LoRa, which there were some talks this week about as well. NB-IoT and Sigfox, those are like, more or less the big players, let's say, in the field. And then we have DASH7. And it's maybe a little bit of an underdog protocol, but it's doing its, well, in terms of competing with the others, it can, get in line as well. So if I want to, why we are using it, basically in our research group, I think we have been using it like over more than 10 years as well. And what I've seen as of use cases is for like localization. We had a few doctorates on that. Crowd size estimation even. For energy harvesting, which is from another doctorate, which was quite recently. Smart metering, of course, and in smart cities as well. I was actually also quite amazed that the standard itself is already 20 years old. As Arnold Schwarzenegger would say, old but not obsolete. So back in 2004, it got ISO ratified. And it originates actually from the ISO IEC 18000-7 spec, hence the name DASH7. Back then, it describes actually the parameters for active air interface communication at 433 megahertz bands back then of RFID. And it was originally actually created for military purposes. That changed a bit back in 2009, where the Department of Defense awarded like, millions of dollars. A contract for DASH7 RFID devices, software, and services to 4 specific companies to make it actually a bit more commercial, to get it out there, to make it more open, let's say. Also in that same year, DASH7 Alliance was announced, which they try to improve and enhance the spec and keep control of it, basically. And they did. And they pointed more into the direction of IoT functionality. As we see to the spec today, we see that it supports all sub-gigahertz bands. It is an open standard for ultra-low power mid-range sensor and actuator communication. And the version 1.2 spec is published in 2019, sorry. And they're working on the version 1.3, I heard, and that should come out quite soon. In cases of, to give some ranging cases basically, we have seen some applications that can go up from 2 to 3 kilometers, but general practical use is about 500 meters where it's used. As I said, it's a full stack. This is to give you an idea of all the layers that it's defined basically. What I want to focus on is really like the file layer, of course, the more tangible layer, let's say, for this implementation. As you also might see, I make here like there's a bit of a gap between the two top layers and the other 5 layers. That's where the ALP layer, application layer, protocol layer, can be used for other technologies as well, for example, for Bluetooth, because it's quite a generic implementation, actually. And then, of course, you have the DASH7 Alliance specification of the stack, which is quite specific only for DASH7, of course. as I mentioned, the Alliance protocol is an open source communication standard for mid-range communication. So basically, it also fixes the gap between the short range and the long range technologies. So it fits quite neatly in that. Looking further into the spec, it's a quite simple binary GFSK modulation that it's using. Most of the time it's GFSK. It has also FSK, but yeah, for normal purpose, not really used. The unlicensed bands, of course, the 423, 868, and here in America, the 915 band, which is used. It also describes 3 channel classes, the low rate, normal, and high rate. Name is a little bit self-explanatory, of course. You can put more bits the higher you go. What I used for my implementation is more the low rate. You can go also normal and high rate if you want, but that's basically playing with a bit more bandwidth and some parameters you need to change, of course. Also for my application, I come from Europe, so I used the 868 megahertz band to play around with. It has like a span of 7 megahertz, so can do quite a lot in that. And it also, the spec itself, if you look into it, it supports 2 sync word classes, we call it. That depends on which type of frame you're using. Background frames use typically sync word class 0, whereas foreground frames use class 1. Also, the sync word itself, it specifies the coding scheme that is used. Currently, there are like 2 coding schemes, as you can see. The most used is the PN9, which is the most simple one. It's a pseudo-random sequence scrambler, basically, based on a 9-bit polynomial. So my sync word that I wanted to implement was quite easily picked. Of course, you can start using more advanced coding schemes as well if you want to, but I did not look into that. So, of course, we need to send data. We need to define how our packet is actually looking like. The spec defines it like this, as most of the technologies. A preamble starts. It has a sync word and a packet payload. The preamble and the sync word, they are non-encoded. The packet payload itself, of course, is encoded with the PN9, or the PN9 with half a FEC. These fields are used for time synchronization, frame synchronization. The payload itself, it starts all the way with a 1 byte payload length. Of course, the data itself, and it adds a CRC16 at the end of the packet. Okay, so we can start building on our transmitter. I put it into 5 steps, quite common steps actually, which I implemented. Again, our frame, as you see. I use this multiplexer in GNU Radio with some vector sources where I can literally define my fields very easily. I do my mapping, so from 0 to 1 to 1 minus 1, basically. Simple mapping for GFSK, of course. Of course, the most interesting thing here is that I have the coded packets where I use the Python module, which does the PN9 scrambling and the CRC16. Going forwards, so we see this as the output, 0s and 1 in our packet, mapped to 1 minus 1. We literally see very clearly our, excuse me. So this was the flow graph, our unmapped bits and our mapped bits. Continuing to creating our symbols, our literally waveform, of course. We use a Gaussian shape filter, basically. So we upsample our symbols, or bits, sorry, our map bits, and we do some pulse shaping with a Gaussian filter, which we can define. You can find it very easily online, how the definition goes. And the most interesting characteristic here is the beta, which is the bits to symbol time rate, which basically defines the shape of your pulse, which is, quite important. So here you see like the definition of it, how I did it in GNU Radio. You can play around with the parameters, of course, but I try to follow the standard to the specification as good as possible. And we get our pulse-shaped sequence. For the baseband modulation, I use another block, an IIR filter, and so we need to integrate our symbols. In discrete time, we have to do that, so we have to find a way. We do that with an IIR filter with specific taps. We convert that to our complex value, which we feed then back to our SDR eventually. So what we see as an output, we see our space and mark frequency nicely popping up, which is a good result already. You can use any type of SDR, of course, to do this. Of course, it needs to have a certain amount of bandwidth for that. In this case, I used channel 0 to transmit on, following the channel classes, of course, of DASH7. When we look at the spectrum, we also see nicely the effect of GFSK and just FSK usage according to bandwidth usage. Also from the top, you see literally more energy at the left side, less energy, more concentrated on the right. Then the receiver itself, basically the reverse operation that I did. 6 steps I define here. So the down conversion, the reception, demodulating, time synchronization, frame synchronization, and of course the payload decoding. SDR reception, I made a small mistake here. The transmitter, it can be a much more smaller sample rate, but of course because we use narrowband frequencies, frequency band. And of course at the receiver side, I really want to check at the full spectrum, the 868 band, to know if there is at least a signal in that band. You can do that, of course, wireless or wired. Then the down conversion, simple multiplier that I use, which is tuned to the center frequency of channel 0 in my case. I low pass filter that a bit to reduce some noise. The demodulation itself, as I said, reverse operation. We try to extract the phase. We take the derivative. Instead of integrating, we derive. We filter a bit because that interpolating FIR filter, that way of deriving, implements extra peaks we don't want in our spectrum, so we filter that out. High frequency peaks. Then I cropped up the time, frame synchronization, and payload decoding in one other parts to make it more clear. The time synchronization I do with a symbol sync you might be familiar with. I use a Mueller and Mueller timing error detector. You can, of course, use early late as well, or some else, something that at least outputs one sample per symbol. And if you also look quite good there, I apply a filter bank, which is also my matched filter that I apply. After that, I correlate my stream with I try to find the preamble, of course, and the sync word again in my stream. I add a tag to that to just visualize it better, basically. After that, then the heavy load starts. I do the PN9 decoding again. I check the CRC again if everything works fine or not, and I put something to the logs of the console, basically, of GNU Radio. And of course, hopefully, I get all my bits back. I did some experiments with this, be it in a wired setup. I used a very cheap board for that. You can also, with that board, you can also do LoRa or Sigfox, so it's quite, a wide usage, basically. I set up a DASH7 node, a transmitter, and a gateway to log effectively, to see if my packet is really received, if it's really correctly decoded. And I saved all those samples with my USRP to disk. I used one attenuators there. Here I used another payload. The payload can be up to 256 bytes, 65 bytes, sorry. The sample rate itself here is 7.68, again, to have the full band, of course. And then saving to a certain format. setup that I had on my bench. I even, this is then the output that I get. I use 3 channels, channel 0, channel 93, and channel 186, to have one, more at the left, at the right, and in the center, more or less. Should give the same result, of course, right? 30 packets, and I could all recover them, of course, because it's a very controlled setup, wired, not that much can go wrong. And to check that if everything went wrong, you could look at the time domain, of course, at the console logs, and I put them here in bold. What you nicely see here is that my packet is, more than the bytes I defined. That's, of course, caused by the complete stack, which also add extra minimum frames, let's say, minimum fields to that payload in order to be seen as a real DASH7 packet, of course. But if you look closely, of course, in bold, I can get my message, which is 00ABCD in hex, back again. The 2 last bytes are the CRC. So everything went right, the CRC went correctly, so my packet is completely correctly received. I even continued that further with some experiments, indoor and outdoor. I'm not going to share the results with you. Of course, it was a bit worse. In terms of results, you have line of sight, non-lines of sight, multipath effects going on. But it was a quite interesting test. So I conclude with that I build a system that completely works. I can investigate packets, and the idea is also to, in the future, implement more parts of other layers, of course, to even investigate further on how it works. Of course, implementing the 1/2 FEC is also an option I can add. If you want to search for the files, they are all online on GitLab. The dataset is also published on Zenodo. It's in the SIGMF format, so you can check it with engine very easily. And if you want to know more about the DASH7, all the links are there. Contact, of course, if you want to contact me. So thank you for your attention. And if there are questions,